All right, welcome back. In this lecture, we begin looking at the process of estimating a simple linear regression model using observed data. This process is called fitting the model, and the goal of the process is to find an estimated model that fits the observed data the best. This requires specifying a criterion that defines what we mean by best. There are several ways of doing this. We will look at two such criteria in this lecture, and we will visually fit align two sample data using each criterion. We will see that the different criteria result in different best lines. So here's an overview of what we'll be looking at in this lecture. We'll start off by reminding ourselves of the canonical form of the simple linear regression model. We will then identify the parameters of the simple linear regression model. Those are the parameters that need to be estimated. We'll talk about the parameter space of a parameter. We'll then introduce notation for estimators. We'll then look at an introduction to the concept of estimation, and we'll introduce criterion functions for defining what it means for an estimated line to be best. We'll look at two specific criterion functions, the sum of absolute errors, or SAE, and the sum of squared errors, or SSE. We'll then find the line of best fit for a particular data set by optimizing each of these criterion functions visually. So let's first remind ourselves of the canonical form of the simple linear regression model. Recall that the word linear in the name linear model means that the model is linear in the parameters. A regression model can be highly nonlinear in the explanatory variables and still be a linear model. For example, the regression model given here, y equal to beta 0 plus beta 1 times the square root of x plus epsilon, is clearly nonlinear in the explanatory variable x. But because it is linear in the parameters beta 0 and beta 1, it is still a linear model. Now note that while the deterministic component in the model above is nonlinear in x, it is linear in the variable w equal to the square root of x. This is easily seen by substituting w in for the square root of x, which results in the model y equal to beta 0 plus beta 1 times w plus epsilon, which is clearly linear in w. We see that this representation has the canonical simple linear regression model form. So, the first model above involving the square root of x is a linear model because it is linear in the parameters. In addition, it's a simple linear regression model because it is a linear regression model that contains only one explanatory variable. Now, because of this, in our development of procedures for simple linear regression, we can, without loss of generality, work with simple linear regression models expressed in the canonical form shown here, y equal to beta 0 plus beta 1 times x plus epsilon, in which the deterministic component is linear in the explanatory variable x. And we can speak of finding the line of best fit. Again, this is because any simple linear regression model possessing a deterministic component that is nonlinear in the explanatory variable can always be re-expressed in terms of a derived variable with respect to which it is linear. Always keep in mind, however, that linearity in terms of the explanatory variable is not what makes a regression model a linear model. Next, we're going to be looking at two distributional characteristics. Next, we're going to be looking at two characteristics of the distribution of the response variable in the simple linear regression model. In particular, we're going to be looking at the mean and the variance of the distribution of the response variable. So the canonical form of the simple linear regression model, as we know, is given by y equal to beta 0 plus beta 1 times x plus epsilon. Now, before we can determine the mean and the variance of the response variable, we need to consider the mean and the variance of the model error term. The model error term, epsilon, is a random variable with unknown variance, which is denoted as var of e, the variance of e, or epsilon, as well as sigma squared. Now, one of the assumptions in standard regression analysis is that the variance of the error term does not depend on the value of the explanatory variable x. This is why, in the notation above, the variance is not subscripted. Now, whether this assumption is true in a particular experimental real-world situation needs to be checked as part of the overall data analysis. This will be discussed in detail when we talk about evaluating model adequacy using residual analysis. Assume that the form of the linear regression model has been specified correctly. That is, that there are no other terms involving the explanatory variable x that need to be included in the deterministic part of the model. If this assumption is correct, then, without loss of generality, the expected value of the error term, that is, the mean of its distribution, can be taken to be 0. This is because if its expected value were different from 0, the model could be re-expressed in terms of an equivalent model with an error term possessing an expected value of 0 and an intercept and/or slope coefficient that captures the non-zero mean value of the original error term. Let's see what we're talking about notationally. There are 3 situations to consider. First, suppose that the expected value of epsilon is equal to some non-zero constant, which we'll denote by a. That is, the expected value of the error term is equal to a non-zero constant, and which, because its constant, does not depend on the value of the explanatory variable x. The original model can then be re-expressed in the following way. So the original model, y equal to beta 0 plus beta 1 times x plus epsilon, can be re-expressed as beta 0 plus a plus beta 1 times x plus epsilon minus a. So you see here we have a plus a and a minus a. They cancel out. And then we can rewrite that as beta 0 star plus beta 1 times x plus epsilon star, where beta 0 star is equal to beta 0 plus a, and epsilon star is equal to epsilon minus a. Now, using the linearity property of the expectation operator, the expected value of the re-expressed error term, epsilon star, is given by the following. The expected value of epsilon star is equal to the expected value of epsilon minus a. That's equal to the expected value of epsilon minus a. Now the expected value of epsilon is a, so we have a minus a, which is 0. And so we see that the re-expressed model does indeed have an error term with an expected value of 0. Next, let's suppose that the expected value of the model error term is proportional to the value of the explanatory variable x. So for example, the expected value of epsilon is equal to b times x, where b is some non-zero constant. the original model can then be re-expressed in the following way. So the original model, y equal to beta 0 plus beta 1 times x plus epsilon, can be rewritten as beta 0 plus beta 1 times x plus b times x plus epsilon minus bx, and that can be re-expressed notationally as beta 0 plus beta 1 star times x plus epsilon star, where beta 1 star is equal to beta 1 plus b, and epsilon star is equal to epsilon minus b times x. Now again, using the linearity property of the expectation operator, the expected value of the re-expressed error term is the expected value of epsilon star equal to the expected value of epsilon minus b times x. That's equal to the expected value of epsilon minus the expected value of b times x. All right, now the expected value of b times x is just b times x because both b and x are constants. Okay, the explanatory variable here is assumed to be measured without error, or we're doing a conditional analysis on the value of x. All right, and so the expected value of epsilon, as given above, is b times x, and so the expected value of epsilon star is b times x minus b times x, or 0. And so again, the re-expressed model has an error term with an expected value of 0. Now, by the linearity property of the expectation operator, the third case to be considered, in which the error term is a linear function of the explanatory variable, so for example, the expected value of epsilon is equal to a plus b times x, this scenario is covered by the application of the previous two results. So it follows then that without loss of generality, the mean of the model error term can be taken to be 0 in all of our subsequent development. And let me also just point out that the re-expressing of the model would never actually have to be done explicitly by us. That happens automatically through the calculations involved in estimating model parameters. Now, let me just also point out that this discussion that we've just had about the mean of the error term being taken equal to 0, that is predicated on the original underlying assumption that the form of the linear regression model has been specified correctly. That is, that there are no other terms involving the explanatory variable x that need to be included in the deterministic part of the model. Now, whether this assumption is true in a particular experimental real-world situation needs to be checked as part of the overall data analysis. This will be discussed when we talk about evaluating model adequacy using residual analysis. So we can now determine the mean and the variance of the response variable. Note first that the distribution of the response variable y depends on the value of the explanatory variable x. Denote the mean of the conditional distribution of y given x by this notation here, lowercase Greek letter mu with y vertical bar, which is read given, and then x all in the subscript. So again, we would read this as mu sub y given x, the mean of the conditional distribution of y given x. This is also called the expected value of y given x, which is expressed using the expectation operator in the following way. So capital E for the expectation operator of y and then vertical bar x. And again, that vertical bar is our conditioning vertical bar, so y given x. And using the linearity property of expectation, this value is found to be the following. So the expected value of y given a value of x, which is also denoted as mu sub y given x, is equal to the expected value of the quantity beta 0 plus beta 1 times x plus epsilon. And that is equal to, using the linearity property of expectation, the expected value of beta 0 plus beta 1 times x plus the expected value of epsilon. Now we just got done showing that the expected value of epsilon can be taken to be 0. In addition, the expected value of beta 0 plus beta 1 times x is just beta 0 plus beta 1 times x. And so the mean of the conditional distribution of y given x, also called the expected value of y given x, is equal to the deterministic part of the model evaluated at that x, beta 0 plus beta 1 times x. Using properties of variance for a particular fixed value of the explanatory variable x, the variance of the conditional distribution of y given x is denoted in the following way: var of y given x. And so that is equal to the variance of beta 0 plus beta 1 times x plus epsilon. And again, using properties of variance, that's just equal to the variance of the error term, which is denoted by sigma squared. Now again, this result is true if and only if the constant variance assumption of the model error term is true. Next, let's identify the parameters in the simple linear regression model. So again, here is the canonical form of the simple linear regression model. In this model, we have observed variables and we have unknown model parameters. So y and x are the observed variables. Y is the observed response variable. X is the observed explanatory variable. And then beta 0 and beta 1 are unknown parameters. So beta 0 is the intercept of the deterministic part of the model, and that parameter is unknown. Beta 1 is the slope coefficient in that deterministic part of the model, and it's unknown as well. Now the epsilon, that is an unobservable random variable, and the variance of the error term, as we know, is sigma squared. And so there are three parameters in the simple linear regression model. We have the two beta parameters, beta 0, the y-intercept of the deterministic part of the model, and we have beta 1, the slope of the deterministic part of the model. Finally, we have sigma squared, which is the variance of the model error term, sigma squared. Now the beta parameters need to be estimated first. Once we have those estimators, then we can estimate the error variance. Now these parameters are unknown and must be estimated from the data, the xy data, I going from 1 to n. Next, let's talk about what we mean by the parameter space for a set of parameters. So the set of allowable values that a parameter can take on is called the parameter space for that parameter. In the simple linear regression model, there are no restrictions on the values that the beta parameters can take on, so that in general, beta 0 can be any real number between minus infinity and positive infinity. Likewise, beta 1 can be any real number greater than negative infinity and less than positive infinity. In addition, the only restriction that the model places on the error variance is that it must be non-negative. So sigma squared must be greater than or equal to 0. Now we can also think of the parameters in the simple linear regression model as the components of a three-dimensional parameter point, which we will denote here by theta. theta being the ordered triple, beta 0, beta 1, and sigma squared, being a point in three-dimensional Euclidean space. The parameter space is then that subspace of three-dimensional Euclidean space, R3, where beta 0 can be any real number, beta 1 can be any real number, and sigma squared can be any non-negative number. All right, next, let's introduce some notation for estimators. Now, it will be necessary that we differentiate between the parameters in the model and the estimators of those parameters in our notation. We're going to use what is called hat notation to do this. In particular, estimators of the parameters beta 0 and beta 1 will be denoted using the same lowercase Greek letters but wearing hats or carets, so that beta 0 hat will denote an estimator of beta 0 and beta 1 hat will denote an estimator of beta 1. In the same way, the estimator of the error variance, sigma squared, will be denoted by sigma hat squared. Hat notation will also be used to differentiate between the mean of the conditional distribution of the response variable y given the explanatory variable x, which is denoted mu sub y given x, or the expected value of y given x, and its estimator, which is obtained by using each of those pieces of notation but putting hats on them. For the simple linear regression model, y equal to beta 0 plus beta 1 times x plus epsilon, once estimators beta 0 hat and beta 1 hat of the beta parameters have been obtained, the mean of the conditional distribution of the response variable y given the value of the explanatory variable x is obtained by plugging the estimators beta 0 hat and beta 1 hat into the deterministic part of the model as follows. So mu hat sub y given x, which is the same as the estimated value of the expected value of y given x, which is also denoted as beta 0 plus beta 1 times x with a big hat over that whole thing. All right, that is equal to beta 0 hat plus beta 1 hat times x. So that is the three leftmost pieces of notation in that bottom string of equalities. That's notation representing the estimated mean of the conditional distribution of y given x. And the expression on the right-hand side, the far right side, is how we actually calculate it. The point predictor of the response variable y for a single observation with explanatory variable x will also be denoting using hat notation by putting a hat on y. Now, the estimated mean of the conditional distribution of y given x will be used for this predictor so that y hat, the predicted value of the response variable y at value x of the explanatory variable, will be equal to the mean of the conditional distribution of y at x. In other words, y hat, which again is the predicted value of the response variable y at a given value of x, will be set equal to the estimated mean of the conditional distribution of y given x. And that is equal to beta 0 hat plus beta 1 hat times x. All right, now let's talk about estimation. So what is it? Estimation is the data-based process of selecting from the parameter space values for estimators of model parameters that are best in some sense. In the context of simple linear regression, we can think and speak of the process of estimating the model as finding the, quote, line of best fit, end quote. Now let me just say parenthetically here, as discussed previously, even if the deterministic component of the simple linear regression model is not linear with respect to the explanatory variable, the model can always be re-expressed in canonical form in terms of a transformed or derived variable with respect to which it is linear. And so because of this, we can always speak in terms of finding the, quote, line of best fit. Now, to do this, to find a line of best fit, this requires a criterion to define what is meant by best. Intuitively, it's desirable to select estimators of model parameters that produce predicted values of the response, y hat, that are close to their corresponding observed values, y. Now, one possible criterion for evaluating candidate lines is the number of points through which the candidate line passes. With this as the criterion, one could define best as the line passing through the greatest number of points. Now, for any data set with 2 or more points, one will always be able to find 1 or more lines going through 2 points. In fact, with n points in the data set, there will be up to n choose 2, which is n times n minus 1 all over 2 such lines. Note, however, that there is no guarantee that a line will exist that goes through more than 2 points. This will be the case when there are no sets of 3 or more collinear data points. So let's look at an example of this. We'll call this example 2.0. It's not in the textbook. And the possible criterion that we're using here is the number of points through which a candidate line passes. So consider the data set on the next slide containing 10 data points. What we're going to do is visually evaluate the fit of a few candidate lines using as a criterion the number of points the line passes through. Note that for 10 data points, there are 45 lines passing through 2 points. Some of these may be duplicates if there are 3 or more collinear points. So here's the data set. It contains 10 observations, 10 data points. And here is a scatter plot of that data set. So we can see here that the data exhibit an increasing trend between the response variable y and the explanatory variable x, and that the relationship looks fairly linear. And so simple linear regression would be reasonable in this situation. So let's look at some candidate lines. So here is one possible line. This line goes through 2 of the points, but I'm sure that you would agree with me that it does a horrible job of predicting the rest of the observed data points. It would do a good job of predicting the 2 points that it goes through, but it would do a horrible job of predicting most of the other data points. Now, in addition, it has a negative slope, which is the opposite of the increasing trend shown by the data. All right, this line goes through 3 of the observed data points, and it does follow the increasing trend of the data. But while it fits those 3 data points very well, it badly misses the rest of the data points. This line also goes through 3 of the observed data points, but again, it does a poor job of fitting the points that it does not go through. Here's one more line that passes through 3 of the observed data points. This one seems to do a better job than the previous lines. In addition, it looks better to me because it seems closer to more points overall than the previous lines. Now, this example demonstrates several problems in using the number of points that the line passes through as a criterion. The first problem is that even though a line may pass through 2 or more data points, that in and of itself does not guarantee that it will be close to the rest of the points in the data. So while it would be a good predictor of the points it passes through, it would not necessarily be a good predictor of the points that it does not pass through, nor would it necessarily be a good predictor of future observations. Secondly, denote by K the greatest number of data points that are collinear in the data set, that is, that lie on any line. There may be more than one set of K points in the data set that are collinear, that is, 2 or more distinct lines passing through K points. And so this criterion does not guarantee that it will return a unique line. And if there were 2 or more lines going through K data points, which line would we choose to use? So this example suggests that a more global criterion would be preferable. In other words, a criterion that takes into account the closeness of a line to all of the points in the data set. Let's look at this idea in the context of our example data set. So this is a continuation of example 2.0, and we're going to be measuring the closeness of a line to a set of points. What exactly does that mean? How can we quantify that? How can we quantify how close a particular candidate line is from a set of points? So here again is our data set of 10 observations along with our scatter plot. And so what we want to do is to measure the closeness of a line to a set of points. And so let's look more closely at our scatter plot. And let's think about superimposing a candidate line over our data. All right? And then looking at how close each point is from the line. So again, the idea is that we want to select a line that is as close to all of the data points as possible. This requires measuring the overall distance of a candidate line from the data, which in turn requires measuring the distance from each point to the line. The distance between 2 points is well defined and is given by the Euclidean distance between the points. Given that a line consists of an infinite number of points and has infinite extent, how can we measure the distance from a point to a line? Now, one approach would be to measure the perpendicular distance from the point in question to the line. However, in regression applications, that's not the approach that we take. Rather, the distance from a point to a line that we will use is the vertical distance between the observed point and the line. And that is the distance between the y values. And so we see that represented here where we have drawn the vertical lines from each of the points to the candidate line. Now, the distance between the observed and predicted values for the ith experimental unit is given by the absolute value of the difference between the observed value of y sub I, and the predicted value of y, that is the y value on the line, which is y hat sub I. So these absolute values for each of the data points, and again, here is the picture. All right, so the length of each of those vertical line segments joining the observed data points with the candidate line, each of those absolute values gives us the distance, the vertical distance from each point to the line. And so the criterion function that we're going to come up with is going to involve those distances in some way. Now, there are two possible criterion functions that use all of these distances. The first is the sum of the absolute errors. So it's the sum of those absolute values, and we're going to call that SAE, the sum of the absolute errors. And so that is just the sum of these distances, the sum, I going from 1 to n, of the absolute value of the difference between the observed value of y sub I, and the predicted value of y hat sub I. The other criterion that we can use that is based on these distances is obtained by squaring those distances and then adding those squared values up. And that is called the sum of squared errors, or SSE. So that is the sum, I going from 1 to n, of the square of the absolute value of the differences. And we can also express that as the sum, I going from 1 to n, of the square without the absolute values. All right, so you can express that either way. So those are the two criterion functions that we're going to be looking at that give us more of a global measure of how close a candidate line is to a given data set. And the idea then is that we want to, using each of these criterion functions, we would want to optimize each of those two criterion functions. In other words, we would want to find a line that minimizes the sum of absolute errors. And we would want to find a line that minimizes the sum of squared errors. And so let's do that for this data set. All right, we'll have a demonstration of this, and then we'll come back and wrap up the lecture. All right, so we're going to be fitting a line to our data set visually, and we're going to fit a line to our data set using each of our two criterion functions. We're first going to use the SAE, the sum of the absolute error criterion function, to fit a line to our data set. And then after we do that, we'll use the SSE, the sum of squared errors, to fit a line to our data set. And so we have our data set here on the left-hand side in this table. And then we have a graph, a scatter plot, of the data points over here on the right. So the blue points correspond to the data points, and the green line is the candidate line that we're going to be adjusting to fit our data set. Now, because the data points are represented in blue in the graph, I'm going to put a blue box around the data points in the table. And because the candidate line is represented using green in the graph, I'm going to use a green box to outline the predicted values, the y values, on the line. Now, I'm going to use a red box to outline the deviations between each observed value y and the predicted value y hat. So these are the absolute values of those differences. And then we get the SAE, the sum of absolute errors, by adding up the values in that column. And so since those are red, I will put a red box around the SAE value as well. So you can see that currently the value of the SAE is 2.6. Now the parameters in this line, the green line, are contained here in this little table, the candidate parameter estimates. And because the line is green, I'll use a green box to outline the slope and the intercept for the candidate line. So again, the goal is to find the best fitting line using the sum of the absolute errors as the criterion function. We're going to optimize SAE, and what that means in this case is we're going to at least try to find a line that minimizes the sum of the absolute errors. And so what we need to do here is we need to move this line around so that it has a slope that corresponds with the observed trend of the data, so that would be an increasing trend. And we also need to adjust where it intersects with the vertical axis. And so to do this, I'm going to first play around with the slope of that line by clicking on this up and down arrow here. All right, and I'm going to increase this until it appears to be fairly parallel with what would seem to be the trend line, or the trend in the data. So maybe about there. And then I'm going to adjust the intercept so that the line goes through the cloud of data points. Okay, so maybe about there. All right, so once we get the line fairly close to where we think it needs to be, we also need to keep an eye on the value of SAE over here. All right, and then we can fine-tune the parameter estimates to get that line situated in such a way that we minimize the SAE. And so you can see that we currently have an SAE value of 1.7520. And so let's see if we can play around with this line. Okay, and decrease that SAE value. And so you can see here by adjusting the slope, I'm decreasing it a little bit, that the SAE value is decreasing. Okay, it went back up there, so let's keep it at 0.84 for now. We may adjust it a little bit more. Okay. Let's see here. Maybe if we decrease this a little bit. Okay, so you can see here that the SAE value is decreasing. Okay, it's still going down a bit. Okay, so it looks like the minimum value of SAE is going to be about 1.65, and that occurs when the intercept is 0.13 and the slope is 0.75. All right, so we can go up here and let's just put those values in. So the intercept of the best fitting line according to the SAE criterion, the intercept value is 0.13 and the slope is 0.75. And with those values, we get an SAE value of 1.6500. All right. Next, let's do the same thing using the sum of squares error as the criterion function. And so we start off again with our candidate line being horizontal with an intercept of 0.5, which is the mean of the response variable. We could start it off anywhere, but this is just where I happen to be starting this. And so this time what I'll do first is I will decrease, well, that's not what I wanted. I'll decrease the intercept. Right? We know that it's going to have to intercept down here somewhere less than 0.2, it appears. And then I'm going to, from there, increase the slope. And we can see the value of SSE decreasing as we bring this line more in line with the data. Okay. And so let me go back up here to the intercept. I can see that I need to decrease that a little bit. So that looks like it might be about right. And so now let's keep our eye on SSE. All right, so I'm going to increase the slope a little bit, and that did decrease the SSE. All right, continuing to increase that slope, and if we look at the graph visually, it does look like it needs to increase a little bit. And so let's keep doing it. Let's keep our eye on the value of SSE. Okay, so when I'm at 0.8 for the slope, we have an SSE value of 0.3474. If I decrease the slope, that increases SSE. And if I increase the slope from 0.8 to 0.81, that also increases the SSE. Okay, so it looks like the best fitting line according to the SSE criterion has an intercept of 0.07 and a slope of 0.8. So let me go ahead and enter those values. Okay, so we fit two lines to our data, one line for each of our two criterion functions. All right, so this line here is the least squares line, or appears to be, based on our visual fitting, along with looking at the value of SSE. This would be called the least squares line, or the least SSE line. All right, an intercept of 0.07, a slope of 0.8, and that gives us a value of the SSE of 0.3474. And that is the minimum value that we were able to find by searching lines using our visual fitting technique, where we're tweaking the two parameters, the two beta parameters in the model. Now, this line is slightly different than the least SAE line. Let me toggle back to that line, and you can see, we'll be able to see the line change. And so you can see that the least SAE line has a little bit higher intercept, all right, and the slope is a little less. And that gives us a minimum SAE value of 1.65. Now, obviously, the values for the minimum SAE and the minimum SSE are really not comparable. All right, so we really can't evaluate or compare the SAE versus the SSE using those values. They're just not even comparable. But for a given criterion function, either the SAE criterion or the SSE criterion, okay, we can compare for example, we can compare the SSE values between different lines. And we can compare different lines with regard to their SAE values as well. Okay, so this just demonstrates how we can visually fit lines to data using these criterion functions. One thing I also wanted to point out was that, and we see this visually. Okay, let me again toggle between the two lines. Okay, so this is the SAE line. This is the SSE line. And so again, we see that they're pretty close, but they're not exactly the same. And so the two criterion functions do give us different lines, as we would expect. Now, one thing I wanted to point out, to show you, is that if we were to evaluate or calculate the value of SAE for the minimum SSE line, the least squares line, what do we think is going to happen to that value of SAE? Is it going to be the same, or is it going to decrease? Is it going to increase? Well, let's check it out. Okay, so the minimum or the slope of the least squares line was 0.07. So let's put that in. And the intercept, the slope, so the intercept was 0.07, the slope was 0.8. Okay, and so if I toggle back and forth between the two graphs here, we see that those lines are the same now. Okay, but notice that the sum of the absolute errors for the least squares line is 1.7000, which is greater than the SAE value for the minimum SAE line. Okay, the minimum value of SAE is 1.6500, and that was obtained by the minimum SAE line. And so we can see that the SSE criterion, or the line that minimizes the SSE criterion, does not minimize the SAE criterion. All right, and likewise, and let me adjust this back to the proper values for this criterion. Okay, so now we're back to the minimum SAE line with an intercept of 0.13 and a slope of 0.75. All right, and we see the SAE now is again 1.65. And so toggling back and forth, we see that those lines are different. All right, now let me change the intercept and slope here to the values that minimize the SAE criterion function. All right, and so that was 0.13, and the slope was 0.74. Okay, and again, let me toggle. Let me see here. Oh, I see. It's actually 0.75. There we go. Okay. So when we toggle back and forth, okay, we see that the lines are coincident now. All right. So look at what happens to the SSE, the sum of squared errors, when we evaluate that quantity at the SAE line. All right. So a line with an intercept of 0.13 and a slope of 0.75. The sum of squared errors for that line is 0.3620, which is greater than the minimum value, the minimum possible value of SSE, which was 0.3474, which was obtained when the intercept was 0.07 and the slope was 0.8. And so we see that the SAE line, the best SAE line, does not minimize the SSE criterion function again, and we would not expect it to. So the point of all this, this last part, is to just show numerically that the two criterion functions, obviously they're mathematically different, but optimizing one criterion function does not optimize the other. All right, and so because of that, that is why we see these different lines, right? When we toggle back and forth, we can see that minimizing the two criterion functions results in different lines. All right, so that's what I wanted to demonstrate with this little spreadsheet. How to, just the idea of fitting a line, finding a line of best fit, right? To do this, it depends on the criterion function that we're using. I think it's pretty clear that this process is or could be fairly time consuming. It doesn't scale well. If we had more than one explanatory variable, it would become extremely difficult, if not impossible, to do this. If we had 3 or more explanatory variables, we wouldn't even be able to represent it graphically. All right, we would have more slope coefficients. We would have a slope coefficient for each explanatory variable in the model, so we would have to be adjusting all those, and it would become very tedious and probably impossible to find the plane or hyperplane of best fit, because when you've got one explanatory variable, all right, the graph is a line. If we had 2 explanatory variables, then the surface that we would be fitting would be a plane. If we had 3 or more explanatory variables, it would be a hyperplane in however many dimensions that correspond to the number of explanatory variables. And so it really would not be possible to even visualize that. So we need a different procedure, a different method of finding the line of best fit or the plane of best fit. And we're going to be looking at that in the next lecture.